proper in those parts. And that selected area diffraction aperture is used so that all the beams coming are just excluded and only the ones falling upon the relevant crystal and then coming out of that crystals are selected, and you get a highly interpretable, visible and resolvable diffraction spots on the imaging screen. Objective stigmatism, image stigmatism and diffraction stigmatism. When you take an image from a moving thing and the blurriness occurs. So stigmatic images are also like that. If stigmatism is there, those whose eyesight is impaired, when your eyesight is not perfect, remove your glasses and look into the moon, it will appear stigmatic, right? It will have some circles or edges which are not actually coming from there, but they are coming because of the stigmatism of your eye lenses. And diffraction stigmatism is also the same thing. The spots will appear blurred. These are two very important points: depth of field and depth of focus. In the optical microscopy, you have a sample, and for example here, it is 100% focused. But when you move a little bit here, that area is either lower or slightly up, slightly lower or slightly up. So this area of the sample is 100% focus, and this area is not, because the light beam doesn't have the depth of focus. And the benefit of electron microscopy is it has the depth of focus. So when you focus the beam, then it is not a single plane which is on focus, but if there are depths and humps, they are equally in focus. And this is because the depth of field. The depth of field. So instead of the perfect focus here, an area here and an area here, they are also in focus. In the electron microscope, in optical they are not. So when you are taking an image in the optical microscope, it is very difficult to have a homogeneous sample throughout, and your one area of the image appears very well focused, but the other out of focus, and scientifically, technically, that image is wrong. Either you will have to take image only from the focused area and then enlarge it for your requirement, or you will have to make the sample 100% plain throughout so that everything is simultaneously in focus. Because the light beam, the light microscopy has no depth of focus. Here, slight below and slight above are also in focus, and this is the skill of the benefit of the electron microscope. So the depth of field is the range of distance at the specimen parallel to the illuminating beam in which the object appears to be in focus. So it is the range of distance. The range of distance from the focus. It is exactly focused here, and if it is here or slightly above and it is in focus, then you call it the depth of focus. And the depth of field is also but at the image plane. The range of the distance at the image plane, when you focus the beam to this screen, and this screen is slightly lowered or moved up, and it is not in focus, then your whole process of microscopy was lost. When you are looking into something and you are focusing, and slight movement up and down changes the focus, then your whole microscopy has gone. You will see the image in proper focus here, but when you image onto the photographic camera, right, that will not be in focus. And that is the benefit of the electron microscopy, that if you have that depth of focus and depth of field, it allows you to take the images slightly down and slightly above the exact focus. And that which I was talking of, phase contrast microscopy, where you see fringes. If you go into the high resolution microscopy and further detail, it is called Scherzer defocus, slightly defocusing the beam to see, to enhance the resolution, to make the features which are not visible. And why it comes at very high magnification? If I have this sample and this is the image, and there is a thin area which I can't distinguish, so when I slightly defocus it, then the difference appears. And when it is properly focused, I can't see it. And at very high magnifications, people are using Scherzer defocus for those sort of image analyses. I'm just telling you the visualization of what happens in microscopy. When you go into the book, then you will properly use the technical terminology and words there, and you will further systematically go into these things, right? The condenser lens, now I am just showing you piece by piece that it is a parallel beam of electron coming onto the condenser lens. And I have time and again tell you that this lens is not the glass lens, but people are showing it just for similarity with the optical microscopy. So they give that shape as a conventional lens. So this beam comes and it is condensed by the condenser lens. The role of the condenser lens is to make the beam that is striking the sample as nearly parallel as is possible, right? Then as magnification increases, the condenser lens must be adjusted to properly illuminate. When the magnification increases, what does this mean? And how you visualize it? You have a light in the room that is emitting electron, right? In the center of this roof, you have a light. When you raise the light up and up, when it is at the level of this roof, it will illuminate only this room. But when you take it upwards and upwards, the light will go fainter and fainter, right? The light will appear to disappear when you take it up, and to such a height that there will be no illumination here. And that illumination is retained by the condenser lens. So it is keeping the beam in such a way that even if you take it higher and higher, still enough light is falling, enough beams of electrons are falling onto the sample, onto the top of the sample. So it must be adjusted to properly illuminate the specimen. When the lens is brought to its small spot, the beam is said to be at the crossover point. Look at that. That here, left of the crossover, and that is the center minimum beam size, and right of the crossover. So in both cases, left extreme and right extreme, the beam is not focused. And when it is exactly at that position, the crossover is there within that lens, then it is the optimum position. And again, I am telling you that when you increase or decrease the density of beam, they mean by this crossovering, they mean that if this is the screen of the machine and the beam is here, and that is the 100% fully focused beam, right? But what you need a beam spread over in this whole area. You are working with that. So when you focus it onto the center, and by now you can increase or decrease the size of this spot. Increase or decrease the size of this spot. It is spherical here and completely spherical here when you reach the edges of the screen. Then this is focus. That you increase or decrease the size of the spot and it doesn't move to the sides. This means the condenser lens is focused. If it moves, then it is defocused. But you never use the machine at this spot because it burns the screen. You spread the beam to the whole screen. And when you are going to the very high magnification, as I told you, at low magnification and high magnification, all these components behave differently. So when you are going to very high magnification, this means you spread the beam to that level. When you spread the beam, this means you decrease the intensity. And you will not be able to see things on the screen if you leave it like that. And for that purpose, you put the aperture so that only selected beams are coming and you can resolve features. Less light is there, and that less light must be, and the microscopy rooms are always dark. You never keep lights on in the microscopy room in order to see things properly. It is very important, right? I am time and again telling you that I usually, if you look into the slides, sometimes during speaking I do mistakes, right? Instead of field emission, I say thermionic emission. And I put notes on the videos that here field emission, not the field emission, but thermionic emission should be written. If you check that, then I make my corrections. So when you read book, then obviously if I say something wrong, you will be able to correct that. So book is very, very important.